Hello everyone, I'm Huang Liham, and I'll be presenting on improving deep learning-based optical music recognition for camera-based inputs. An overview of my presentation is as follows. First and foremost, an introduction to the topic. A music score is a visual representation of how a piece of music should be played. It consists of various notes, text, and symbols that act as instructions for music performers. Optical music recognition is seen as a counterpart of the more acclaimed optical character recognition, which seeks to translate a scanned or printed image of musical scores into a semantic or agnostic form. I will now move on to speak about the background of this research and some related works. Firstly, traditional OMR. Generally, traditional methods predefine some handcrafted features of staves and notes. Those matching algorithms then compare given input patterns with predefined samples and generate the outputs of pitches and rhythms. When the number of data increases, the traditional fails to generalize shapes of staves and notes by handcrafted features, resulting in a saturation in the accuracy. Next, deep learning OMR. Instead of using handcrafted features, the method trains a convolutional neural network to extract features for a given input image, recognize patterns, and build an end-to-end mapping between the image and corresponding pitch and rhythm values. An objective function for the training is based on monophonic scores or polyphonic scores. For both works, the same limitation is seen. The algorithms can process and recognize scanned images or sheet music with a high level of accuracy. However, the recognition performance for camera-based inputs is significantly degraded. Most especially for the TF-deep OMR algorithm, learning an end-to-end mapping without pre-processing steps degrades the performance of the algorithm. To address this problem, we investigate the use of a few well-known filtering techniques to improve the robustness of a deep learning OMR framework, and I will now introduce the methodology. Firstly, pre-processing of a camera input image. Some common pre-processing techniques that have been used in prior work in other fields include Gaussian blur and median filtering. These techniques are most commonly used for edge detection and edge filtering to improve the quality of images used for training and detection to improve the robustness of an algorithm. Next is the proposed OMR framework for camera inputs. In this study, the camera primos dataset is being used. The C primos dataset is an extension of the printed images of musical staves dataset, which has deliberately distorted images to model real-life camera input images. The algorithm used for this work is based on the TF-deep OMR algorithm, which originally focused on the recognition of properly scanned music scores from primos. This work, however, focused on training the algorithm to accurately predict the pitches and rhythms from the camera input distorted or noisy images. As for the TF-deep OMR algorithm, the process in which the model is built is as follows. The convolutional neural network learns the features of the input images, passes them on to the recurrent neural network that consists of long short-term memory architecture before predictions are being made. The connectionless temporal classification is also used to perform local optimization using the expectation maximization algorithm. I will now go on to the experiment, which is based on the methodology introduced earlier and the corresponding results received. Two main experiments that were done are shown above. The accuracy of the results was evaluated as a percentage using the formula shown on the slides. For the experiment, the last 5 models, as well as the model from the TF-deep OMR algorithm, were used. Experimentation of the model was carried out using 4 different test images. It was found that the 36 model had produced the most accurate results and will thus be used. The outputs generated by the TF-deep OMR algorithm and the 36 model were documented. A manual check was then done to identify the mistakes made. These were highlighted in orange. The results of each model were then compared. The results of the experiment are as follows. We demonstrate the effectiveness of the proposed framework. Particularly, it is observed that the proposed scheme improves the accuracy by 11.1% on average for both the clean and noisy datasets. Most especially, our proposed significantly outperforms the baseline method for noisy images by achieving an 8% accuracy improvement. I will now move on to the last part of this presentation, the discussion and conclusion. The improved algorithm had shown strong capabilities and high accuracy in the recognition of music from scores captured with a camera. There were some errors in the generated output, and one possible reason could be the algorithm was trained using distorted and noisy scanned images instead of actual camera-based inputs. Some of the areas for further improvement and research would be the following. Generating datasets that are camera-based instead of distorted scanned images. This will create a training environment closer to the test environment, both in terms of image quality and processing techniques required. Secondly, designing an application that will be able to capture an image or accept an image file input and convert the semantic results into music XML or media file formats in real time. Through this study, we have shown that the training of the TF-deep OMR algorithm with the camera primos dataset alongside algorithmic improvements with the pre-processing of images is effective in generating better optical music recognition prediction results. We conclude that developing optical music recognition algorithms to read camera-based input music scores is plausible and should be further explored. Thank you.